Welcome everybody to week 4, the mathematical part of automated flight. Well, we will be solving differential equations using the Laplace transform. And to solve a differential equation this way, we have 3 steps. One is take the Laplace transform take the Laplace transform of our differential equation, and then we will rewrite the expression so that the Laplace transform of our main variable is isolated, and finally apply the inverse Laplace transform using the table provided in the book. So just to get started, some notation. Let's say we have a function of f, and f will be a function of time. If we take the Laplace transform, we get capital F of s. If we have the Laplace transform of the first derivative of f, we have s times fs minus f of 0, where this is the initial condition, one of the initial conditions of the differential equation. We have the second derivative, and we take the Laplace transform, which is s squared f of s minus s of f0 minus f prime of 0. So these are the initial conditions of the function, so of the function itself and of its first derivative. Any higher derivatives, there's a formula for that, and I'll refer you to the book for this. But we will take a first example. So example 1, I will do 3 examples in this series, and just to give you a general idea of how to do this. So let's say we have, I'll write this a bit bigger, dx dt, and what is minus 2x is equal to 2e to the power of 3t. Now this is a first order differential equation. It is a linear differential equation, and it is also it has constant coefficients. These are the models we will be using also in control theory, but more about that when we talk about control theory. Now, what we want to do is take the Laplace transform of the left side and the Laplace transform of the right side. But I'll break it down into 3 parts. If we take the Laplace transform of dx dt, we will get, hang on, I forgot the initial condition, x0 is equal to 2. So we'll just take the Laplace transform of these chunks. As we know, the Laplace transform is a linear operator, which means we can, if we want to take the Laplace transform of this part, it is the Laplace transform of the sum. So I will just write out the Laplace transform of the different components. This will be s xs minus x0, but x0 here is equal to 2, so we will just simply replace this by 2. The Laplace transform of minus 2x is equal to minus 2x of s. The Laplace transform of our exponential, we can find that from the table. So 2 times e to the power of 3t is equal to, well, this 2 we could take out as well. The Laplace transform of e to the power of 3t is 1 over s minus 3. So this 2 just adds to the numerator, and we get these 3 components. So what do we have if we take our whole differential equation, we will have s times x minus 2. I'm dropping the s in between parentheses. Minus 2x is equal to 2 over s minus 3. And we want to rewrite this so that we have something in the form of x equals some expression. And that expression we will then feed into the inverse Laplace transform. So let's do some calculations here. So we have s times x minus 2 times x. That is s minus 2 times x. This minus 2 I'll take over to the other side. It's equal to 2 plus 2 over s minus 3. This is just arithmetic. So now we can divide by this s minus 2. So we have x equals 2 over s minus 2 plus 2 over s minus 2 times s minus 3. Now, we've isolated x, and we've done step 1. This was basically step 1. And step 2, well, we're halfway there because we're not quite ready yet. We still need to write this into a form where we can take the inverse Laplace transform. So let's continue on. And what do I have to do to rewrite this? Well, I first want to write this as one fraction so that it has a common denominator. So I will write this as 2 times s minus 3 over s minus 2 times s minus 3. So I've multiplied it top and bottom with s minus 3, and we have plus 2 times s minus 2 s minus 3. So now we can take the sum of this. So we have 2s minus 6 plus 2 will equal 2s minus 4 over s minus 2 and s minus 3. And so now I have this one fraction, but well, where am I going with this? I want to write this as sum a over s minus 2 plus b over s minus 3, because if we can write it like this, I can use the inverse Laplace transform and I will be finished. Well, it turns out that this particular one, let me just rewrite it. And of course, we know how to do the partial fraction expansion. We could have done that here as well, by the way. But I can write this as 2 times s minus 2 over s minus 2 times s minus 3. And in this particular example, we see that the term s minus 2 here and s minus 2 there can be cancelled out, and we are left with 2 over s minus 3. And if we then take the Laplace transform, because we now know that x is 2 over s minus 3, we want x of t, which is equal to the inverse Laplace transform of our x, which is equal to the inverse Laplace transform of 2 over s minus 3. And then we can look it up in the table, and we get that it is equal to 2e to the power of 3t. So this was step 3. And step 2, we ended up here. Now there are 2 things about this example. Is that so we found the solution to our differential equation. And yes, it was a bit more work here, which we could have started there. Doesn't really matter. But the main thing is that we've already incorporated our initial conditions. Our initial conditions enter the equation here, which means that once we've solved it, there's no need to then fill in some initial conditions to find some parameter. That is all taken care of while we do this. Now in the next part I will show a couple more examples, but this is the main process. We take the Laplace transform, rewrite the expression so that we have something in the form of x, take the inverse Laplace transform, and we have the solution to our differential equation.